All right. Good afternoon. Again, just continuing on with what we have in complex numbers. Again, we have at the foundation, okay, we have the variable I, which represents the square root of -1, and also in looking at converting in terms of the standard form of a complex number, okay, we have I squared is equal to -1, and again, the standard form of a complex number is A plus BI. Okay, now, in looking at what we have working with complex numbers, and I want to mention something about the radicals. Okay, and when you're working with operations between complex radicals, okay, think about complex radicals that you want to go ahead and express the radicals in terms of the variable I. Okay, so we have, when operating with complex radicals, first express the terms or the radicals in terms of I. Now I'll give you some examples here of what we have among operations. And we can take, for instance, okay, we could say we have something like, in terms of adding radicals, we can have, let's say, the square root of -121. And we have plus the square root of -81. Okay, and again, we have square roots of negatives, and those are already going to go to I terms. And 121 and 81, those are perfect square values. Now, the square root of 121 is 11, but that of -121, that is going to be 11I. And for the square root of -81, now the square root of 81 is 9, that of -81, okay, so that is going to be 9I. And if we combine, okay, so we have 11I plus 9I, so we have in the sum, okay, we have 20I. And let's say we're looking at taking a difference of radicals. I'll give you a couple that, okay, that we have inside. Okay, we have the opposite sign of numbers that are not perfect squares, but whose square roots can be reduced. Okay, let's say we have something like the square root of -48 minus the square root of -300. All right, and if we express the radicals in terms of the variable I, okay, now before the reduction, we can go ahead and write each of these. We have the square root of 48I, and we have subtracting, and we have the square root of 300 times I. And in terms of these numbers here, now 48, not a perfect square, but it is a number that has perfect squares higher than 1 as factors, and the highest perfect square that will go into 48, that is going to be 16. And 16 will go into 48 3 times. So if I draw out, you can see we have square root of 16 times the square root of 3, and you have I alongside. And for the square root of 300, the highest perfect square that is divisible into 300, Okay, that would be 100. So we can express as the square root of 100 times the square root of 3 times I. And we have in the reduction, okay, so we have square root of 16 is 4. And we have times the square root of 3i. Then we have minus. Now square root of 100 is 10. We have times the square root of 3i. Okay. Now we have, with these terms, we have the same number inside the radical. Okay, so these are like where they both have the square root of 3 and I. And looking at the leading coefficients, 4 and negative 10. And if we take the difference, we're going to have negative 6 times the square root of 3 times I. And you could also write this as negative 6i times the square root of 3. Now, in the case of what we have among our other operations in arithmetic in the complex numbers. Now, in terms of adding and subtracting, okay, it's not difficult to remember to rewrite in terms of the letter I. And I would say probably if there's any operation where it is easy to overlook, it would be the operation of multiplication. And let's say that if we have, like multiplying together, let's say we have the square root of 9, make that square root of negative 9, and we have times the square root of negative 4. Okay. And again, so if I express the radical in terms of I, okay, I'm just going to take this out just a little bit further. So you have the square root of 9 times I. And we have with the square root of negative 4, so I have the square root of 4 times I. Okay, so we have 3i times 2i. And in taking the product, so you have 3i times 2i, so this will be 6i squared. Okay. And remember, I squared is equal to negative 1. So if I were to follow through, so we have 6i squared, so we have 6 times negative 1. And we're going to have, for the result, okay, this will come out to negative 6. And the reason I'm saying that this is perhaps the hardest to remember in terms of drawing out the letter I is that there's the temptation. Now we have two radical expressions in the same root. You have square root and square root. And there's the temptation to multiply negative 9 and negative 4 together. And negative 9 times negative 4 is a 36. And again, the square root of an expression cannot reduce to a negative constant. And the square root of 36 would have been 6. But you're not going to multiply negatives right away. And instead of multiplying the negatives inside the same radical, you're going to go ahead and draw out the I. So again, negative 9 has a square root that goes to 3i. Negative 4 has a square root that goes to 2i. And again, we have for this result, we have not 6, but instead negative 6. And that's thanks to the i's that factored out. Okay. And now, for what we have in the case of what we have with division, and we have, let's say if we have, in this case, if I have something like the square root of negative 16 all over the square root of negative 25. Okay. So for what we're going to have here, okay, so you have like square root of negative 16. You can write that as 4i already. I'm just going to kind of draw this on out. So have the square root of 16i all over the square root of 25 times I. And so the square root of negative 16. Okay, if you already have it as 4i, and square root of negative 25 already as 5i, that's fine. And for what we have in terms of the follow through, okay, so you're going to have the I factors that cancel out. And so for what we will have in the result, okay, that will reduce to 4/5. Okay, so just looking at items, if you're looking at square roots that contain negative terms, and we're dealing with and operating with them along the lines of adding, subtracting, multiplying, or dividing, and if you have that, any of those types of run-ins, you want to go ahead and factor out the I. Now, for what we have in the case of numbers, and we sort of looked into a brief application the other day, and this is going to be for what we have in the case of complex conjugates. Okay. And for what we have, again, just regarding complex conjugates. Again, so we have with these. Okay, now again we had the standard form of a complex number is a plus bi. And in the realm of dealing with conjugates, again we have that the conjugate of a plus bi is going to be a minus bi, and you can reverse that statement. And say that the conjugate of a minus bi is going to be a plus bi. Okay, so you're going to have, say if you have an a term, that's going to remain fixed between the conjugates, but for the I terms, okay, they are going to be additive inverses. And let's say that if you have, in the case of categorizing, say you have a number and you want to determine what the corresponding conjugate will be. And we'll say that we have, first of all, if we have something like a number in standard form. So we'll say we have 4 plus 3i. Okay, so you have an expression of addition. So a is at 4, bi is going to be at 3i, and now the complex term is added. And in the conjugate, okay, the only difference is that you're going to have subtraction of the complex term. Okay, so you have 4 plus 3i, and the conjugate will be 4 minus 3i. So that which represents sort of the real part, that is the term or the value that does not have I alongside, okay, that will remain fixed. It is only with the I terms that you're going to have a change up. And if we have something like, let's say we have negative 3 minus 6i, okay, now the conjugate, now we have negative 3, okay, that will represent our a, that remains fixed. And for minus 6i, you have the operation of subtraction, and the conjugate is going to be consisting of the operation of addition. So the conjugate of negative 3 minus 6i will be negative 3 plus 6i. And let's say that if we have, say just a number, if we have like the number 17, well, 17 doesn't have I alongside it, so 17 would represent a, and in the conjugate, okay, a is going to remain fixed, So if the number has only 17, well, the conjugate is just going to be 17. And as for what we have, let's say you have the number given as, and we'll say that we have negative 14i. Okay, well, the conjugate here, okay, you're going to take the opposite sign of the I term, okay, and there's no indicated term in A, just where we have bi is given as negative 14i, and the conjugate is going to be a positive. Okay, so throughout, a number and its conjugate will consist of the same A values, but with the I terms, okay, we're going to have, again, an additive inverse relation, where one is positive, the other is negative, and vice versa. Now, for what we have in the case of conjugates, okay, the product of two conjugates is going to be a real number. And just for instance, okay, say if I have, say just with the first pairing, okay, so you have 4 plus 3i. You have times the quantity of 4 minus 3i. Okay, so for these conjugates, if I FOIL out, say 4 times 4 is 16. And we have with the outside product, you have 4 times negative 3i, so we're going to have a negative 12i. And then inside, you have 3i times 4, so this will be a positive 12i. And the I terms are going to cancel out. And we have with the last product, so we have negative 9i squared. Again, first order I terms cancel. Okay, so we have 16. Now for what we have concerning minus 9i squared. Again, we have I squared is going to be negative 1. And so this is going to be carried over. And so we're going to have 16 minus 9. And for I squared, again, so you have times negative 1. And negative 9 times negative 1, so this will be a positive 9. And for the result here, we're going to have 25 in the end result. Okay. And if there were any other way to display this, I had to give the I term, just depending upon what is asked for. If I had to give what represents bi explicitly, representing 0 would just be 0i. Okay, still, the result translates to 25. All right, and in the case of conjugates, we have let's see. And we say we have a complex number fraction. Can be converted to a plus bi form. That is the standard form. And this type of conversion is possible by using the conjugate of the denominator. And we can take, for instance, if I were to express, let's say 2 over 3 plus I, in a plus bi form, so for what I have here, say got 2 over 3 plus I. Okay. And now, in terms of converting, okay, so we can convert a complex number fraction, which this is, by using the conjugate of the denominator. Okay, now here for 2 over 3 plus I, the denominator is 3 plus I. Okay, so we have that the conjugate of 3 plus I is going to be 3 minus I. And in terms of using this conjugate, so we have with 2 over 3 plus I. Okay, now we're not dealing with like the least common denominator, but the follow-through will have the same kind of exercise if I'm writing a fraction in terms of the least common denominator, in the sense that I'm going to take this ratio and I'm going to multiply by 1 in the form of the conjugate divided by itself. And so we have with this approach, okay, so we have 2 over the quantity of 3 minus I. Okay, so 2 times 3 is 6. 2 times negative I is going to be a negative 2I. And for, again, we have 3 plus I, 3 minus I, and the product of conjugates is just going to be a single real number. So here we have 3 times 3 is 9, and you're going to have the outside and the inside products to cancel. So we have the outside product is at negative 3I, and the inside product, okay, we're going to have at positive 3I. And for the last part, we have negative I squared. Again, we're going to have the terms in the middle to cancel out. And right now we have 6 minus 2I. We have 9 minus I squared. And again, I squared is going to be at negative 1. Okay, so you have 6 minus 2I. Now for 9 minus negative 1, this will be 9 plus 1, which will be 10. And if I'm looking at expressing this number in a plus bi form, so for a, we have right now we have 6/10, and for bi I have minus 2/10 of I. And for the coefficients, okay, we can reduce, and so we have, in the case of 2 over 3 plus I, in the reduced a plus bi format, okay, this is going to come out to 3/5 minus 1/5 of I. Now, and looking at what we have just from the page 80 sets, and again, so just kind of going back to what we have with working with radical terms in the form of square roots of negative amounts. And for what we have in the leadoff, okay, so we're looking at the square root of negative 10 times that of negative 5. Okay, again, okay, before you do anything like make the careless error of multiplying negative 10 and negative 5, understand the tendency to do that since we had the same radical type in the square root. But again, if you see a negative inside the radical, and with the radical being a square root, okay, you want to go ahead and factor out I. Okay, so you have the square root of 10I, and for the square root of negative 5, okay, so you have the square root of 5I. Now, you can multiply the numbers inside the square root, okay, if we only have these values to be positive. Okay, so you have the square root of 10 times the square root of 5. Okay, this is going to be the square root of 50. And I times I, okay, so this will become I squared. Okay, and for the square root of 50, okay, again, not a perfect square value, but this one can be reduced. Where we have the square root of 25 times the square root of 2. Now again, I squared is going to be at negative 1. Now we have the square root of 25, okay, that would be 5. We have times the square root of 2. Again, we have multiplied by negative 1. Okay, so we have 5 times the square root of 2 times negative 1. And this result is going to be negative 5 times the square root of 2. Okay, and so in this case, they have the product of two complex square root numbers will very likely yield a negative real value. And this is what we have here with negative 5 times the square root of 2. Okay, now, and what we have for number 18, okay, and we have for this one, okay, so we're looking at the operation of division. Now, there are technically different ways you could go about this. Now, for the fraction, we have the square root of negative 80, and we have all over the square root of 5. Okay, now, again, so you have just the square root of negative 80, okay, with the negative sign. Now, the square root of 5, okay, 5 is positive. And again, if I were anything that we have in complex notation in the radical, you can go ahead and factor out the I. And so we have, since we had the square root of 5, there's no letter I to factor out. So right now we have the square root of 80 times I all over the square root of 5. And there are various ways that you can go about following through. And so we have with the square root of 80, okay, so I can reduce. Now 80, not a perfect square, but it can be factored. And the highest perfect square divisible into 80, okay, so that is going to be 16. So you have the square root of 16 times the square root of 5 times I. And we have all over, okay, the square root of 5, okay, and between the numerator and denominator, okay, we can cancel out the square roots of 5. And so we have the square root of 16I and for the square root of 16 multiplied by I, And we have in the final result, in this case, this would become 4 times I. Now, and looking at what we have with 42 and 50. Now we're looking at expressing the results in the standard A plus BI form. Okay, and in 42, okay, so we're looking at taking a number that is already in standard form with 10 minus 3i. Now we're going to be looking at squaring. So for 10 minus 3i quantity squared, kind of like when we were working with squares of binomial expression, it'll be that expression times itself. Okay, so we're going to have 10 minus 3i times itself. And setting up what we have here. So we have 10 times 10. That is 100. And then for the outside and inside products, okay, these will each be negative 30i. And we have with the last product, okay, so you have a positive 9 times I squared. Okay, so and following through, okay, so we have 100. Now negative 30i minus 30i, so we're going to have a negative 60i. And for 9i squared, so you got plus 9, I squared becomes negative 1. Okay, so you have 100 minus 60i minus 9. And then for the standard format, okay, so we can come out to 91 minus 60i. For what we have in the case of 50, okay, and now this is going to be an instance, okay, where we have conjugates that are involved. And for what we have in this one, now we have radical terms in the mix. Okay, so you have the square root of 5. Okay, we have plus the square root of 7 times I. And then we have the square root of 5. And we have minus the square root of 7 times I. Okay, now I'm going to FOIL out once again. So we got conjugates, okay, because you have the same A term, and the BI terms are going to be additive inverses. And if I take the FOIL, now the square root of 5 times itself would go to 5. But I'm just going to put this in radical terms at the moment. Okay, so I have the square root of 25. Then for the outside product, we have positive times the negative is a negative. Okay, now we have inside, we had positive square root of 5, positive square root of 7. I can multiply together, seeing we had the subtraction of the square root of 35. We have times I. Inside, I have addition. And square root of 7 times the square root of 5. So this will be the square root of 35. Again, I have I to be attached. And we have with the last product, we have positive times the negative is a negative. And square root of 7 times the square root of 7, so this will be the square root of 49. And I times I, so this will become I squared. And so we have, looking at first product, again, you have the square root of 25, and that's already going to be at 5. Now for the second and third items, the outside product, inside product, okay, there's going to be additive inverses. So these will go out. and we have square root of 49. Okay, got 7. And I squared goes to -1. Okay, so we're going to have 5 minus 7. I squared again goes to -1. And -7 times -1 goes to +7. And 5 plus 7 is equal to 12. And again, if I had to express this in any other way, I think the author probably has the result in this form, where you have the BI term included, which again is going to be negligible, or in this case 0i. All right. Now, regarding what we have in the case of where the conjugates are going to be utilized. Okay, now 50, you're looking at, again, the product of conjugates can be reduced, okay, to a whole number or an integer. Now, for what we have in the case of number 51, okay, so we have a fraction. Okay, so we have 6 plus 2i. And we have all over 3 minus I. And again, we have with the denominator. Again, you have the conjugate, which is going to be 3 plus I. Okay. So if I take what I have in the ratio, okay, so I have 6 plus 2i all over 3 minus I. Okay, now we got a standard form in the numerator, standard form in the denominator. But if I make this fraction as a standard form, complex number in its own right, we're going to have with the pathway to create, and this will be multiplying this overall ratio by 1 in the form of the conjugate over itself. And if I go ahead and distribute, okay, so with the FOIL, if I take the FOIL of the numerators, so I got 6 times 3 is 18. Outside product have 6 times I. Inside I have 2i times 3, so we have another 6i. And the last part we have 2i times I, so this will be 2i squared. And for what we have in the denominators, okay, so you got 3 times 3 is 9. And again, the outside, the inside products will be additive inverses. And the last product, so we have negative I squared. And we have for following through, so we have 18 plus 12i. Now again, 2 times I squared is at -1. We have 9 minus I squared, so we look at 9 minus -1. And here we have 18 plus 12i minus 2. We have all over 9 plus 1. Or by then you can go ahead and write as 10. Okay, so we have 18 minus 2. We have in the numerator. Combining, we have 16. And we have with our I terms, so we have plus 12i. And we have all over 10. And separating, okay, so we have 16 tenths. Now you can reduce and then separate. but I'll do it in this fashion. Okay, so right now we have our A term is at 16/10, and this ratio can be reduced to 8/5. And for the B is at 12/10, and that is reducible as well. And we can get this down to 6/5. And so we have, for the result, we have with the ratio 6 plus 2i all over 3 minus i, and expressing as one number. Okay, that is in standard complex form. Okay, we're going to have 8/5 plus 6/5 of I. And now, little change up, and we have, in the case of taking what we have for 52, okay, so you have 5 plus I over 4 minus I. Again, we have with the denominator a 4 minus I. Okay, so the conjugate, okay, this would be 4 plus I. And just taking what we have in the ratio and multiplying by 1 in the form of 4 plus I over itself. Okay, so we have with the FOIL, so we have 5 times 4 is 20. Outside product we have at 5i. Again, inside product we have at 4i. And the last product, okay, so this is going to be positive I squared. Again, this is going to translate to the subtraction of 1. Again, in the denominator, okay, so you got 16. Yeah, plus 4i minus 4i minus I squared. And again, in conjugates, okay, the outside and inside products will cancel. So here we have 20. 5i plus 4i becomes 9i. And I squared we have at negative 1. And in the denominator case, you have 16 minus, and I squared again we have at negative 1. Okay, so for what we have in the numbers, 20 plus negative 1 is going to be at 19. And we have plus 9i. And 16 minus negative 1 becomes 16 plus 1, which is 17. And once we separate, okay, so for the A, that is going to be 19 over 17. And we have plus bi, and that is going to be 9/17 of I. Okay, and those fractions are already in simplest form. Okay, so again, 5 plus I over 4 minus I translates out to 19/17 plus 9/17 of I. Okay, now for the next set of terms, and there might be a slight feeling of redundancy for these, and we have only single terms in the denominators. And here we have in 55. Okay, now we got the fraction 5 over 13i. Again, with 13i, okay, so the conjugate is going to be negative 13i. And if I take what I have in the ratio, multiplying by 1 in the form of negative 13i over itself. Okay, so again we have the original ratio. You have times negative 13i over itself. And 5 times negative 13i, so this will be negative 65i. 13 times negative 13, this will be a negative 169. And I times I, so this will be I squared. Okay, here we have negative 169. I squared we have at negative 1. Okay, so we have negative 65i. Negative 169 times negative 1, so this will be a 169. And for what we have here, okay, is that we can reduce this ratio, and we undid the presence of 13i. And the conjugate, the purpose of that is mostly to just undo the I in the denominator. Okay, but that 13 is going to recycle. For that is going to be the greatest common factor of both the numerator and denominator. Okay, because you have like 13 will go into negative 65i, negative 5i times, and 169, that is going to be 13 times itself. So we have 13s to cancel out. So for the reduced form that we have here, it's going to turn out that 5 over 13i will translate out to the negative 5/13 of I. And if there were another way to express this, like in the explicit a plus bi form, that is, you have only an I term, so your a value would be at 0. So the other display would be 0 minus 5/13 of I. All right, now for 56, different number in the numerator and denominator, but the nature of the problem, you still have a single I term in the denominator, and that 7 is going to be used repeatedly. Okay, now for 7i in the denominator, okay, so the conjugate would be negative 7i. Okay, so if I use the conjugate for this ratio, so I have 6 over 7i. And we have times 1 in the form of, again, the conjugate over itself. And so multiplying, so we have negative 42i. And 7 times negative 7, so you have negative 49. And you have I squared. Again, for negative 49, I squared, so you have negative 49 times negative 1. So you have negative 42i all over 49. And again, this ratio can be simplified for, we're going to have that 7 to be reused, and 7 is going to be the greatest common factor of the numerator and denominator. So for negative 42i, okay, we have 7 times negative 6i, and for 49, Again, we have 7 times 7. Okay, so we have a set of 7s to go out. And so for 6 over 7i, okay, this will become negative 6/7 of I. And again, if I had to give the a explicitly, this would be 0 minus 6/7 of I. All right, now in the crossover and still working with complex numbers. Okay, now we've looked at terms, just like, or if I had operations, okay, like adding, subtracting, multiplying, and dividing. But let's say if you're looking at solving for a variable in the complex number system. Okay. And so here we're going to have equations with complex roots. And just an instance here. Now, when we were looking at solving for a variable, along with linear equations, and we had the categories like conditional, contradiction, identity, and then we crossed over to solving quadratic equations. And again, we had among our techniques, we had the zero product property, as well as the square root property of equality, as well as the quadratic formula. And these techniques will also roll over into this type of equations, okay, where we have complex roots that will be involved. And let's say if we have, for instance, if we have an equation, say we have x squared plus 4 is equal to 0. Okay. Now, if I had a difference of squares, I can say I have the quantity of x plus 2 times that of x minus 2 is equal to 0. But now with the sum of squares, I cannot factor into real integer coefficients. Difference of squares, yes, but a sum of squares, I cannot. And some might be, well, could it not be x plus 2? Well, here's the deal. If I were to take x plus 2 and square out, again, you have x plus 2 times itself. And I've seen some make the mistake, like take x squared plus 4 and say it's, and once they try to come up with an attempt to square root property of equality, would that not be x plus 2 times itself, or x squared plus 16, would that not factor out to x plus 4 times itself? And the answers would be no. And the reason for this, if I took like the square of x plus 2, this would be x squared, and you have plus 2x plus 2x, which would be 4x, and you have 2 times 2, which is going to be 4. Now we do have the x squared and the 4, but notice we had the missing first order x term. Okay, so x squared plus 4 does not factor out as x plus 2 times itself, because you already have the missing 4x from the get-go. So in terms of looking at solving for x, so what I can do is separate the x squared apart from the 4. And so what I can do here is I can move the 4 over by subtracting. And so I'm going to have the x squared is equal to negative 4. And running on a course where we're going to have where we already had the setup where we can utilize the square root property of equality. Again, so you have x squared is equal to p. We have the x equal to plus or minus, okay, the square root of p. Okay, so for x squared equal to negative 4, if I go from x squared to x, So we have x is equal to plus or minus, okay, the square root of -4. And now, while the square root of 4 is 2, that of -4 is going to be 2i. So for x, we're going to have additive inverse complex roots with plus and minus 2i. Okay. Now let's say if we have a case where we're still going to have complex roots, and we'll say that we have here that we have the square of x plus 36, I should say x plus 1 squared. And we'll say we have plus 36 is equal to 1. Okay, so I have the square of x plus 1, and if I were to, once again, just like I moved the 4 over, I'm going to move the 36 over. And just isolate the variable expression. Okay, so we have the square of x plus 1 is equal to -35. Okay, and once again, just in this setup, I can utilize the square root property of equality. So I have x represented by x plus 1, okay, which is squared. And if I go from second to first order, or just plain x plus 1, to the right, I'm going to have plus or minus the square root of -35. So right now I have x plus 1, and rewriting this set of complex terms along the lines of the variable I. So we have plus or minus the square root of 35 times I. And looking at solving for x, so I'm solving for x, not x plus 1. So I can do here, just kind of show you the format, thinking along the lines of, say, just laying it out in terms of horizontal addition and subtraction. Okay, so I'm applying -1, and I'm going to do likewise on the other side, but I'm going to put this out in front of the radical set. Kind of like what we did first time around, weeks back, with when we looked at the square root property of equality applications. And for taking away 1, now we're going to have in compact form, there will be two solutions of x. We have -1 plus or minus the square root of 35 times I. Sorry about that. Okay, so I have -1 plus the square root of 35i, and -1 minus the square root of 35 times I. Okay, now okay, as long as you, if you have like plus or minus square root 35i, or square root 35i minus 1, or negative square root 35i minus 1, I don't know if Alex would pick it up, but they would technically be correct. But normally, The traditional layout would be to have the constant in front of the radical. That would be just the traditional notation, but technically you could have the -1 to follow. It would not be a typical display, but it would be technically correct. And let me mention something too. Now we have with complex roots. Now let's say if I have something like x squared is equal to -20. Okay, so if I go from x squared to x, say with the square root property of equality, now I have x equal to plus or minus, okay, the square root of -20. So I have x equal to plus or minus, okay, the square root of 20 times I and now we have here now 20 not a perfect square number, so I'll just do this on the side here. So for the square root of 20, 20 is not a perfect square number. However, it can be reduced, and among the perfect squares we have 4 is going to be the highest perfect square, and the square root of 4 is 2, and we have times, okay, the square root of 5. So we have in compact notation, okay, we have the x equal to plus or minus 2 times the square root of 5 times I. And just drawing separately, so you have x equal to 2 times the square root of 5 times I. And also we have x equal to the negative of 2 times, okay, the square root of 5 times I. Okay. Now we have just a case of where we have a set of complex roots. And let's say if we have something like 7x squared plus x plus 3 is equal to 0. Now this trinomial cannot be factored into real integer coefficients. Okay, but we can use, let's say it's a recourse, the quadratic formula. Okay, so you have a at 7, b at 1, and c at 3. And we have with the quadratic formula, okay, we see we have negative b plus or minus, okay, the square root of b squared minus 4ac all over 2a. So for negative b, I have negative 1 plus or minus, okay, and I have the square root. Now for b squared, okay, so I have 1 squared we have minus 4 times 7 times 3. And we have all over 2 times 7. And we have in the follow through, so you have negative 1 plus or minus. Okay, we have the square root. Now you've got 1 squared is 1. Negative 4 times 7 is negative 28. Negative 28 times 3 is negative 84. And we have all over 14. And so we have negative 1 plus or minus. Okay, and we have the square root of negative 83 all over 14. And I'm going to leave the results in compact form this time around. So you have negative 1 plus or minus. Now for the square root of negative 83. Now 83 is a prime number, and 1 is the highest perfect square that will go into this. So we're going to have negative 1 plus and negative 1 minus the square root of 83 times I all over 14. Okay, and tell you what, just for the next few moments, I'll tell you what, let's see what we get with the following equations. And we'll say that we have x squared plus 100 is equal to 0, and we'll say that we have the square of x minus 10 is equal to negative 250. Okay, so for the next few moments, let's see what we get for x in both of these equations. Now for what we have with these equations, okay, now we have, for the first, we have a sum of squares with x squared plus 100 set equal to 0, and if I set this up, whereupon I have x squared by itself, so I'm going to move the 100 over by subtracting. Okay, so we had the x squared is equal to minus 100. And just taking what we have now, so we have going from x squared to x, and we have with the square root property of equality, okay, so I have x equal to plus or minus, okay, the square root of negative 100, and the results will be two complex solutions. In this case, we're going to have positive and negative 10i. And for what we have in the other problem, okay, so we have the square of x minus 10 set equal to negative 250. Okay, and here I can go ahead and apply the square root property of equality. So if I go from the square of x minus 10 to just x minus 10, so I have is equal to plus or minus the square root of negative 250. And here we're going to have x minus 10 equal to plus or minus the square root of 250 times I. Okay, and again, 250, not a perfect square, but it is a composite number, okay, whose square root can be reduced. And the highest perfect square that will go into 250, okay, that's going to be 25. And the square root of 25 is 5, so for what we have in following through, okay, so you're going to have the x minus 10 is going to be equal to plus or minus, and we have 5 times the square root of 10 times I. Again, for what we have in isolating x, so if I add 10 to both sides, okay, and we have upon doing so, okay, so we have x, and we're going to have equal to 10 plus or minus 5 times the square root of 10 times I. Okay. And again, if you were to write the solutions separately, we say we have 10 plus 5 times the square root of 10 times I, as well as 10 minus 5 times the square root of 10 times I. Okay, so we have exclusively complex roots resulting from these equations. And for what we'll be looking into next time tomorrow, okay, now so far we've had, with the conditionals, first time around we had just exclusively real values, and this time we have exclusively complex values in the roots. And for what we'll be looking into will be those equations that will have a blend of both real and complex roots. And again, so we'll be looking into this tomorrow. Okay, so for the Alex homework, section R5, the radical absolute value equations portion, that would be due tonight. And again, the class activity 1 set is due Saturday night. And again, that is accessible through Alex. And for the next Alex homeworks from sections R6 and R8, okay, those will be due next week. R6 due on Monday, R8 due Wednesday of next week. And again, I do have video simulations for those items inside the weekly notes tab of Blackboard. And again, just working with the upcoming types of equations, we have on page 81 numbers 57, 58, 61, 68, 71, 92, and number 94.